Hello, this is the Refrigeration Progress Presentation, and the team members are Aite, Jacob, Yanni, and Claudia. We are going to be presenting on these topics. Project Introduction. Machine Chillers Incorporated has developed a cooling system which uses a vortex tube to separate cold and hot air, and a motor as a compressor. The cooling system operates using the reverse Brayton cycle. The objectives are to first model the system and determine its capabilities, and then make recommendations based on the results. The reverse Brayton cycle changes the temperature and pressure of the fluid to selectively remove heat. Starting on the bottom left, air at ambient temperature and pressure enters the compressor, which increases both the temperature and pressure. Then a heat exchanger removes the heat from the air, returning it to ambient temperature. Then a turbine expands the air, decreasing pressure and decreasing temperature. Finally, the cold air cools the load. Equipment. To simulate the reverse Brayton cycle, air enters the system through a pressure regulator, which allows us to set the initial pressure. It then travels to the heat exchanger, where the air is cooled to room temperature. It then goes to the accumulator tank and the vortex tube, which separates the cold and hot air. The cold air passes through a load, which is a block of aluminum insulated by styrofoam. The air is then released. The compressor is not shown here, but to characterize the full system, the setup is changed to pass the air first through a motor, which compresses and heats up the air. The pressure of the air leaving the motor is measured. Method. All temperatures and mass flows are collected for multiple nominal input pressures at steady state and transition state. To characterize the vortex tube, the values of the second half of the system were analyzed. To characterize the compressor was attached before the heat exchanger, such that the values from the first half of the system can be analyzed. Refrigerated load is characterized by calculating the thermal properties of the insulation and comparing it to theoretical values. Once all the steady-state values are calculated, they can be compared to transient data to validate the result.
In order to see the progress of the lab, we needed to characterize each component of the refrigerator. The vortex tube divide the flow into hot and cold mass flow rate, allowing the heat transfer to take place between the reverse steam and the forward steam. The compressor enables the flow of the refrigerant by increasing the pressure at the temperature of the vaporized refrigerant. The heat exchanger and accumulator bring the temperature back to ambient temperature level, with the accumulator trying to even out the pressure regulation from upcoming flow. The refrigerant load is the amount of air the engineer are trying to cool. And all of this was done by transient experiments and data analysis plus the EPA analysis. We made few assumptions during the laboratory, assuming that the heat transfer to the environment was equal to 0. The lump mass model accurately represents the heat transfer of the load over time. The outside of load insulation is at ambient temperature, which implies it's at heat transfer of the ambient temperature, which is small. The volumetric low rate isn't scaled to the ambient temperature and the ambient pressure. The pressure drop across the flow meters is negligible. Since we are using K is equal to 1, we are 62.3% sure that the steady state value falls within the applicable range. Because we do not have perfect sensor, we calibrate the different sensors to account their offset when we want to determine the relationship between the input pressure P3 and the different parameters such as the temperature and the mass flow rate. Finally, the steady state behavior of the temperatures shows an increase in judged pressure rapidly and slowly reaching steady state, keeping in mind that As the input pressure increases, the difference between the mass flow rates increases.
The steady-state data extracted from each of the 0, 20, 40, 60, and 80 psi pressure trials was used to identify trends in the measured temperature, mass flow rate, and the motor angular velocity parameters of the system. Average steady-state values of temperature, mass flow rate, and motor angular velocity for all pressure trials were plotted against the P3 pressure just before the vortex tube. A plot of the T4C temperature located between the vortex tube and the load is located on the right. After plotting the raw steady-state data, both a linear regression and a quadratic fit curve were fitted to the data. It is clear that the data and relationship between T4C and P3 more closely resembles a quadratic fit or other nonlinear fit rather than the linear fit. The T4H temperature measured at the exit of the hot vortex tube end, it was assumed that the pressure difference between the hot end and cold end exits was negligible and that each was equal to ambient temperature. The T4H data shows a much more linear trend and has concluded that this relationship between T4H and P3 pressure is linear. Analysis of cold mass flow rate measured at the cold end exit and hot mass flow rate measured at the hot end exit was performed with the assumption that without input pressure, there would be no mass flow rate and thus m.c and m.h would be equal to 0 with an input pressure of 0 psi. The cold mass flow rate data also shows a very linear trend, and it is concluded that this relationship between m.c and P3 pressure is linear. Hot mass flow rate data did not provide a clear relationship like the other parameters measured. Both a linear and quadratic fit were applied, and neither showed a substantial improvement over the other. Further data points may need to be gathered to assess the relationship between m.h and P3. The compressor motor RPM and P3 pressure at steady state were gathered for compressor pressure values of 0, 20, 30, and 40 psi. The linear relationship identified in the plot on the right provides justification that the relationship between motor RPM and P3 pressure is linear. Using a known value for specific heat of air along with measured values of mass flow rate and T3 and T1 temperature, the rate of heat exchange from the start of the heat exchanger to the end of the accumulator was calculated for 0, 20, 30, and 40 psi compressor trials. The plot on the right represents the gathered data, and both a linear and quadratic fit were applied. While the quadratic fit may connect through more data points, the lack of data points suggests there may be an inaccurate fitting. In any case, the heat exchange clearly increases with P3 pressure before the vortex tube, and it can be concluded that both the accumulator and the heat exchanger are necessary, where the heat exchanger releases the added heat in the air from increased input pressure and motor speed, and the accumulator provides constant pressure at the P3 location.
Now, to summarize our characterizations of the components and the system at steady state, the vortex tube analysis yielded that T4 hot and cold flow mass are linearly related to P3. However, T4 cold and hot mass flow are not, at least linearly, related to P3. They're probably better off fit by a quadratic curve. Now, for the motor and compressor, the motor speed is positively linearly related to P3. And there's little evidence in the data to say otherwise, as it was a long trial from initial pressurization to steady state, and noise was pretty insignificant. For the heat exchanger and accumulator, both seem to be necessary for trials using the compressor, since the compressor produces hot pulses of air that need to be cooled and pressure regulated. Now, the refrigerated load analysis yielded R insulation values for each nominal gauge pressure that range between roughly 2.4 and roughly 3.6. Now we have transient analysis to perform moving forward. We will recalibrate the thermocouples as we did in the steady state analysis and compare the offsets. We will collect T4 cold, T4 hot, T load, and T5 data from pre-pressurization all the way to steady state across that whole span of time. Now, first trial will be using building air at 80 nominal psi, second trial at 40 psi using the compressor. We'll also, once in that steady state zone, find T3 and T ambient as well. with the goal of comparing the building air usage to that of the compressor, mostly to ascertain the validity of Station 3's ambient temperature assumption and determine that assumption's influence on our experimental results. So for the step of propagating error is to find the combined uncertainties of the energy transfer rate of air and the ambient energy transfer rate, which are displayed on the slide and are also simplified using our assumptions from earlier. Same goes for the experimental thermal resistance. We have to, simplify that equation down in order to compute that uncertainty. Now those previous uncertainty values will be used in these equations here, so that for total transient energy we have to compute the combined uncertainty of total heat transfer due to air, shown here, and compute the combined uncertainty of total heat transfer in the equations shown below that bullet point. Again, all have been simplified using our assumptions. Now, all of this analysis was done to answer a few main questions. 1. How well is the system modeled? Q error will be found, which is the discrepancy between the measured and theoretical heat transfer values. And our error propagation will tell us how much of that error is due to uncertainty. We'll also derive experimental material properties and compare those to known values to evaluate model validity as well. We'll also ascertain the capabilities of the provided refrigeration system, namely what temperatures can it reach effectively and after how long can it reach those temperatures. Now we will have more potential improvements as analysis continues. However, all we have for now is to potentially revise the imperfect installation assumption. Here are our references. Are there any questions?